I'm going to, I suppose, a little bit of an introduction as to who I am. I spent 28 years with Overarton Partners, based in the UK, but also in Australia, and also based in Sydney office, Shanghai office for 3 years, and spent a certain amount of time in Hong Kong. So familiar with your particular situation. I've been on the technical committee for the competition, Advancing Net Zero, and on the back of that, asked to talk about some of the things that have been happening in the UK. The UK put into law targeting zero carbon for the whole of the UK a couple of years ago. But before that, we did a lot of thinking about zero carbon, and this is a fairly advanced stage of how we know we're going to get there. So my background, it's 25 years since I started my first zero carbon buildings, and one's been involved ever since in various different kinds of zero carbon, and beginning more to look at embodied energy as well as operational energy. But for now, I'm going to be talking about the UK's trajectory, a science-based approach to how to get to zero carbon, looking at the sorts of policies which we've had to introduce, because it isn't just energy use, and then to focus on the role of buildings and high density cities, because there are many similarities between the likes of London and, for example, Hong Kong, but some very interesting subtle differences as well. This is a slide I've used a lot over the years, and you can see we started looking at reducing our energy use in the UK soon after we had the oil crisis in the 1970s. And since then, we initially looked at 60% reductions, which was introduced just over 20 years ago. We then moved that to 80% when we realized that wasn't going to be enough. And we've now, and this diagram showed that 80% reduction. We had allocations for the different sectors in the community, in the society, because it was realized that different sectors would move at different speeds. Buildings are one of the slow ones to respond and are having to accelerate now. And we moved from 2 degrees to 1.5 degrees. And this is where we have now recently changed this trajectory and put into law the aim for 2050. A lot of the work in the UK has been headlined by the committee, the Climate Change Committee, which is set up by government as an independent arm of government to look at scenarios as to how we reduce carbon emissions and make recommendations for policy. And the law is such that the government of the day has to formally respond to the Committee on Climate Change proposals. We have recently had what is called the 6th budget. You can see the grey steps here over time, which are forecasts for the steps in the reductions. And the government in the last 3 months has accepted the latest 6th budget and now needs to start to put in place policies to be able to achieve that 6th budget, which is for the period from 2028 to 2035. And that's because it takes so long to get policies and regulations in place before you then start to see the carbon savings. Interestingly, we used to not include aviation and international travel. It's that dotted bit on the top there. we have now included in the latest budget, and the government has accepted that we will be including and eliminating the carbon emissions, the net carbon emissions from those as part of our objectives to get to 2050. Now, why the change from 80% to 100%? Well, that's as a result of the Paris Agreement. And if you look to the left here, you can see per person, the UK has had very high carbon emissions. We started burning coal a long time ago, and we put a lot of it into the atmosphere. So we do feel an obligation to pull down our emissions, but to then move into the fastest track to get us down. And we've now decided that actually it's 2050 when we need to be demonstrating it is possible to do it, and it's possible to do it at a reasonable cost. So this is the new budget, which has been adopted by the government, and you can see the next step. And this is what the government is now going to be offering in the COP 26, which is to be held later this year. But on the right, these are two particularly important diagrams. The studies behind this, which used a lot of UK universities and other organizations, have looked at 70 individual scenarios as to how to get to zero carbon, to test out which ones are most cost effective. And down below, we have the cost impacts of going to zero carbon for the route maps they are now looking at, the balanced route map. Above zero are the costs. So there's an initial capital investment, and you don't see savings, that many savings. But by the time we've got to 2050, we are saving more money than we are spending. And this is because that we are no longer having to rely on processes like digging up coal and so forth. Renewables have a lower running cost. For example, transport, the costs of transport drop dramatically because an electric vehicle is typically 80–90% efficient, whereas an internal combustion engine is about 20 to 25% efficient. So this has been looking at the whole equation to try and work out how the UK can get to zero carbon. Before I will move on to buildings. One of the key elements has been understanding offsets and trying to work out what kind of role they are going to take for us in future. In reality, as we get closer to 2050, their use will drop dramatically. We cannot rely on emitting carbon and paying someone else to reduce their carbon, because in a world of zero carbon emissions, no one should be emitting. And what we have here is a graph which shows our carbon emissions falling. Offsets may be used, but they will need to taper and reduce. And by the time you get to net zero carbon, these are sequestrations. These are capture of carbon and locking it away. So standard offsets, as you will often buy, will not be available. And indeed, as every country starts to go zero carbon, they will be using their own sequestration towards their own targets. So at the moment, you find airlines offsetting their carbon because they're growing forests somewhere in a different country. But in reality, that country, when it goes zero carbon, will be looking at that carbon sequestration contribution towards their targets. So understanding the avoiding double accounting means we will lose offsets as we go towards zero carbon. We might be able to use them in the short term, but they will taper very quickly. This is the UK's trajectory, and the mix we anticipate for 2050 for our zero carbon electrical supply. We will need to eradicate entirely our natural gas use, which is predominantly the red one. And one of the characteristics of the UK is we have a very large heating demand in winter, which is obviously different to yourselves. Conversely, you have higher humidity, cooling requirements and things like that. So it's interesting to see the differences between those. You will see our supply. We have sequestration, an element of sequestration here, which offsets some of our grid production, particularly at peak. This is to be grown trees in the UK, so we're expanding our vegetation and looking at harvesting it and then locking in the carbon from emissions of combusting that. So we get a double benefit, and we'll probably for the next 50 years bury carbon emissions into old North Sea oil geology, which is currently now vacant. But you can see buildings, particularly in heat terms, and a lot of our electrical demand in the grey will need to curtail greatly by the time we get to 2050. Now, you might think London's very different from Hong Kong. In reality, in energy use, it isn't. Every one of those buildings you can see there, virtually, is fully air conditioned, despite our mild climate. The solar gain is not that different. You get a fair amount of cloud. We're getting less cloud than we used to with climate change. We're getting more extreme weathers than we used to have drizzle and grey all the time. That kind of weather is now beginning to change. You'll see that most of those are all glass buildings, which has tended to be the way most of these buildings have been constructed, which has resulted in them being a lot more gas guzzlers, using a lot more energy than the predictions would suggest. Large windows may give good daylight, but that does not end up in low energy use, particularly in lighting terms. We tend to find it gets very bright at the perimeter, and then it makes the interior look dark and gloomy. So we're finding that in reality, what happens is not what the modeling has in the past suggested. And our regulations are beginning to now have to change to try and address the fact that these buildings are gas guzzlers. So how do we now move this into the building sector? On the left here, and this is work by LETI, that's the London Energy Transformation Initiative, and there's a lot of these different organizations getting together to try and plot what the targets nationally mean for our buildings. If we're set a target to reduce our demand, how do we do it? But then how much do we do it? We're looking at the 2050 target to taper down the energy use, the carbon emissions, while our renewables begin to rise. We have to look at a point where instead of demand being greater than the supply, we get to a balance. We now then need to work out how much is used by transport, by industry, how much is by buildings, and then start to look at dividing it up between different building types, because different building types can save different amounts. The RAAB is another of these organizations, so the Royal Institute of British Architects, which has been taking a lead, saying we're aiming for 2050, but actually for new build, we need to be looking at far shorter timescales, because we have a lot of existing building stock, which is the challenge in future. new build, we need to be focusing on zero carbon very quickly. And they have been setting targets, working with others, including Letty, including some of the supply side of the industry. And we're now getting to the point where, for example, British Land, as one of our major developers in London, are saying all their future developments will be net zero carbon at completion. And this is because we're beginning to learn how we can do it, but also how we can reduce demand far faster than we have done in the past. And here are the sorts of trajectories we're looking at. And this isn't just prediction, this is measurement. We are about to, there's draft building regulations now being prepared and consultation completed, which are talking about introducing the first stage of you have to measure what your building is aiming to, its energy use, and publish it, so that you can then compare the predictions against the end result. Because to date, other than public buildings, most buildings never had to produce a certificate. And what we've learned a lot from is the Australian neighbours, National Australian Building Energy Rating System, which has started saying, well, don't worry about the predictions. You're going to be judged only on the meter readings at the end. And what's been remarkable is the way they have reduced their energy use compared with the predictions. I'll come back to that a little more. Letty, for example, have published, and it's downloadable, a document, their Climate Emergency Design Guide, which starts to look at what does good look like. In other words, if we've got these targets, and for offices, it's 55 kilowatt hours per meter squared per annum, of which heating is specifically 15, whereas I would see Hong Kong, an element of that 15 would be used for your higher cooling loads and particularly dehumidification. But what this tries to do is tell practitioners the kind of standards, the building envelope air tightness, the U values, the glazing areas. And here you can see, 25 to 40%, as opposed to compared with that image showing those new buildings, which are all glass. This is getting people to realize that there is a fundamental change happening in the way we're going to be designing and then operating the buildings. And I'll go through these in a little more depth. I've touched on some of these, the U values and the target in operational energy terms, the heat recovery, heat pumps used almost exclusively and no more boilers anymore. Form factor, which is the envelope area related to the floor area, is also a key element for reducing the demands. But also embodied energy. Within this, if you're reducing your operational energy, the carbon emissions in the materials become critical. Now, the allocations of national renewables will have some of it going to industry. Therefore, there will be renewables going to those factories which produce materials. But there's an awful lot of other components, like cement, for example, for which we will need to drive out the carbon emissions. We may need to change the chemistry by the time we get to 2050, which we need to do now because it takes so long to test structures to make sure they will last 60 years or what have you. They will do accelerated testing for those. We also are aware that in the short term, we can use cement substitutes, but we need to be very careful because most of them often come as waste from power stations or from blast furnaces, which are unlikely to be available in 2050 as we move away from combustion for generating our electricity supply. We then get to hot water and heating. I won't labor on that for Hong Kong, but demand response is going to be a key element. What is demand response? In the past, if a building needs extra peak demand, it just turns it on and the grid supplies. And the grid has to ramp up a power station somewhere to feed your demand. Come 2050, that will have completely changed. Renewables do not ramp up and down. So there needs to be ways of storing energy, a limited amount, but also to how you run your buildings to be able to reduce demands during peak times. This is what we're calling demand response. In other words, you operate the grid system as a management tool between reconciling supply and demand. And you may get messages from the grid saying, we prefer you not to use electricity at this time. And the idea of maximum demand tariffs being far more punitive, in other words, expensive, to try and get people to design their buildings not to have the peaks simultaneous with the grid peaks. This is the problem we have in the UK. At the bottom, the blue is our electricity demand across a year. This is our gas demand. The red is basically buildings. And you can see that the grid capacity we're looking at for 2050, electrical grid, is about double what we currently have. But it will not be able to serve these heating peaks. We have a major issue trying to work out how to smooth those loads down and make sure there's enough thermal inertia in the building. Maybe there's batteries, other things in that. The grid is looking at using electric vehicles for temporary storage to deal with some fluctuations in the grid. But fundamentally, we have to reduce our demands, our peak demands, very dramatically compared with where we are now. Data disclosure is then the final part of this equation. Just because those big glass buildings in London got a compliance, yes, you satisfy the building regulations and here's the modeling, we found that that doesn't work. And this is where data disclosure becomes a critical part of the way forward. We have to be able to model more accurately. And the only way to model more accurately is to reconcile against the measured results of that construction before and after, and make sure the feedback goes back into the modeling. And what we've tended to find, we've been far too optimistic in the modeling as to how efficiently things work, how systems, control systems work. Most of them don't work as intended, all of those things. And I think you'll hear later a lot more about, in some of the subsequent lectures, about disclosure, monitoring. Those landowners who have gone in and measured properly get a very different result when they then start to look at how they modify the operation of their buildings. And this, in a sense, illustrates it, the situation. On the left here, we have measured values of buildings. This is the European A to E, G labeling of buildings, different colors, and I've put those labels down there. These are measured buildings. There's research been doing, working with landlords to work out how their buildings performed. If you can see, the average doesn't go up as the buildings get to a worse predictive rating. There is something markedly wrong with modeling, whether it's with Energy Plus or SBEM for the building regulations in the UK. They are not modeling energy use. On the right, we have feedback from, I mentioned, neighbours in Australia, where the best in Melbourne of an office building with roughly the same climate as London is using a quarter of the energy that London's average is. In other words, we're using 4 times the best in Melbourne, and certainly more than twice the best in London compared with the best in Melbourne. These we have to learn from and accept, and then change the way we do things. So what does this mean for building designs? And I'm going to finish with a whole set of case studies which are currently being designed, approved, and they've started construction in London. But I'll give you an idea. This is the sort of thing we're looking at. On the left is a typical building, full height glazing, fan core units, cooling load, not far off 130 watts a square meter for your systems. We are now looking at far more modest windows, as I said. We're also looking at the IT. What neighbours in Australia identified, and separate research here, is we are not using anything like the computing power that most of the codes assume we are. And indeed, there are actually advantages in the software of feeding in high tenant loads because it makes your solar loads look smaller. So we found these unintended consequences in the modeling. But if you go through, we're finding that, for example, if we use the new European standard for lighting in workplaces and look at the task lighting option, so this is 300 or 400 lux on the desk for 1 square meter out of 8 or 10 square meters. And the background lighting is at 150 lux. We're then looking at lighting which is halved. Where I mentioned the small power, the computers going down, the solar load dramatically lower. And by the way, the sun angle's lower in the UK. So in mid-season, we get higher solar gains than arguably you will get within Hong Kong. And then there's a fresh air. I would expect that to be doubled, for example, in Hong Kong, given humidity and so forth. But that's your peak capacity, which means your plant is getting smaller. We've now got schemes which are looking at pipes into the ceiling, which then allows us to use a large surface area, which allows heat pumps to work far more efficiently than a fan core unit. We're also finding that we're getting rid of a lot of the kit. The costs of the building can come down. We're also finding the story heights can come down because we haven't got these voids. We don't need the drop ceilings and so on, which tend to have very high embodied energy because they don't last that long. They certainly don't last the life of the aluminium, which a lot of them are made out of. And the cladding area has come down, so we can afford to put more investment into getting the shading and so on, right? So this is a little bit of a snapshot. It's not the only way of doing it, but it gives you an idea. So a number of these little case study snapshots. This is a building going up near London Bridge you can see the centre of the City of London there. The Thames is just going past between this building and those. So fairly large buildings, and we're looking at 55 kilowatt hours per meter squared, which is about 55% better than our current building regulations. And it's what we're calling Paris-proof zero carbon. In other words, if we can bring the loads right down to these levels, we know that as the grid decarbonizes, we will get to a point where the grid will have enough capacity to serve that building 100% with zero carbon electricity. And so we're looking ahead to where the grid is decarbonized, but of a limited capacity, and we are future proofing for that eventuality. This building, in fact, has a fair amount of PV on it, and it's used in the shading. It tends to be the more costly way of being able to achieve these, but you know, cities always seem to have a certain proportion of buildings where more money gets spent on them than others. This is a more pragmatic approach. Underneath this is Southwark Tube Station, the underground. You all know only too well over station developments, of which you in Hong Kong are experts. But this is a new building where once again you can see this number coming up, 55 kilowatt hours per meter squared, 17 stories. This one's also doing 40% less embodied carbon. There's a fair amount of timber going into this building, structural timber, and they're reducing the amount of concrete going into the building. This one, 20-story tower, which had planning approval a year or so back. This one is 75% better than the building regulations. And this is going for 35 kilowatt hours per meter squared, including the tenants. And here is the sort of systems we're looking inside the building. We're looking at what used to be called in the 1980s a Versatep condenser circuit system. That just means the temperature it's working at. And what we're looking at is temperatures in the water between 15 and 28. And we can then, when we're cooling up an area, we can put heat back into the pipework. A heat pump can then heat that up to generate hot water. So you can often get a balance in your buildings. And then the rooftop air source heat pumps do the topping up. And we're finding north side of the building may need some heating and the cooling on the south side. And we're putting it via the concrete. So we've got that thermal inertia in the building. And we can then turn off that plant for the peak hours because there's 2 or 3 hours of thermal inertia within the building. This is another one. Here, once again, 75 kilowatts. They haven't got quite so far, but we're on this learning curve as developers begin to realize how far can we go. This one's particularly interesting, and I've included because of its construction. It has changed fundamentally how we construct buildings. So there's a lot less concrete going in on site. There's a steel frame concrete poured simply into the permanent formwork, but all of it is kit parts so that you reduce the amount of material used and you reduce the embodied energy in the building. This one will be a very interesting building when we see it completed. It's now on site being assembled. This is what we're also beginning to see. This is an existing building, which is now being totally refurbished and is going to be reclad. It's now going on to site. This is British Telecom's old headquarters, very close to St. Paul's, which is just to the right. And the system has been completely reclad, but it reuses all the existing structure and therefore has a very low embodied energy and is once again the targets they're looking at, not quite Paris proof for the whole building, but they're looking at Paris proof for the base build section because some developers are not yet confident they can convince their occupants to lower their energy. And that's one of the things which has been very interesting about the shift to zero carbon the government made in the UK. Psychologically, before that, when we're going to 80%, a lot of people thought, oh, well, I'll be in the 20%. I won't have to do much. Other people will do it. But what we found is once you say everybody has to do it, you can then find tenants are beginning to say, well, I need to do this because my funders and my supply chain are beginning to look. If I want staff, youngsters, they were out on the streets complaining about climate change, the Extinction Rebellion. They are looking for companies which now have good credentials in carbon and energy terms. So the developers are beginning to find that their tenants are asking them how good the carbon of their building is. But developers are also finding new influences. Their funders, the pension funds, all of those funders upstream are now thinking, what's this asset going to be worth in 25 years? If it is a gas guzzler giving out all this carbon, if we have high peak electrical demands and therefore the energy bills are high, we may not be able to occupy it. What's the value of that building going to be in 25 years? And developers are beginning to say, well, actually, I need to anticipate this. I need to be showing I'm the best in the market and attracting that kind of money. With that, thank you very much. I hope you found that interesting, and I look forward to the questions and answers. Thank you.